Assalamu alaikum students, this is Majid Tahir. We are doing computer science lesson number 2, hexadecimal number system. So let's start. So data representation, we have 3 number systems. We have Denary number system, we've already done it in previous lesson. We have binary number system, already done. Today we will do hexadecimal number system. So let's start. Hexadecimal number systems, what are hexadecimal number system? We'll see that. Now we humans, we work with decimal or denary number system. We know that computers, they work with a binary number system. They have to convert everything in zeros and ones. Then why do we need hexadecimal number systems? Let's see. We have already done in the previous lesson hexadecimal number system place values. Let's just quickly see that one more time. We know that hexadecimal number system use numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have A, B, C, D, E, F. What are these A, B, C, D, E, F? These are not numbers. Actually this A, this is for 10, B is for 11, 12, 13, 14 and 15. Why do we use A instead of 10? Because A stores 1 character in the memory instead of 1 0 that will store 2 characters in the memory. So to space saving, we have A to display 1 character in the memory or screen rather than 1 0. It's easy to identify that it's a hexadecimal number system. Now let's see what the place values are. We know that hexadecimal system has, because there are 16 possibilities, we have base 16. The first place value is 16 raised to power 0, that's going to be 1. Always first place value is 1. When we have 16, next place value is 16 raised to power 2, which is 256. Then we have 4096 and so on. It's always a multiple of 16. One hexadecimal system is equivalent to 4 bits of binary. That's very important to understand because we are using 4 bits conversion. Now let's see. We often have to deal with very large positive binary numbers. Let's consider this network interface card, NIC. We have a 48-bit identifier, a long list of zeros and ones. It's very difficult to remember this long binary number, to reproduce this long binary number. So we have to convert this into hexadecimal, which makes very easy understanding the binary numbers. Now let's see. This long binary number is very difficult to convert into denary. If we convert this, we have to do it by using place values. Now 1, 2, 4, 8, 16, 32, 64, 128 and so on. You keep on doing that. It is very huge binary number, so converting into denary is very difficult. Remembering or reproducing this number in binary is also very difficult. So we have to convert these big binary number into hexadecimal number system, which will make it compact. Now let's see how we can do that. Again, this same binary number, when we are going to convert that into hexadecimal number, we are going to group every number into 4 bits starting from the right side. So see, if I'm making this one group, I have to convert that separately. So my place value is going to go to till 8. 1, 2, 4, 8 and 4 plus 2 is 6. So this is equivalent to 6 in hexadecimal. Again 1, 2, 4, 8. This is 3. This is 2. 9. This was actually 1, 2, 4, 8 equivalent to 15, which makes F in hexadecimal and so on. So you see, making groups in 4 starting from the right side, that is how we can convert easily this long binary number into this hexadecimal numbers. Understanding this 00475E7F9236 or remembering this number or reproducing this number is easy as compared to understanding or remembering this zeros and ones or converting them into binary. Let's proceed forward. Conversion from binary to hexadecimal, when we have to convert a binary number into hexadecimal number system, again we just have done the same process in the previous slide. Very easy. You make group of 4 binary numbers, you convert them separately. So 1248 is the place value. One number converted separately makes 7. The other number converted separately makes 5. So this 0 1 0 1 0 1 1 makes 5 7 in hexadecimal number. This is not 57, this is 5 7. Moving forward, when we have to convert hexadecimal number to a binary number, we do the same process in reverse order. For example, we have a number 9F2, which is base 16, which is a hexadecimal number. Now 9 is converted separately, F is converted separately, and 2 is converted separately. So again, 1 2 4 8, we have to convert number 2. So we will write 0 0 1 0, which gives 2. Again 1 2 4 8, we have to convert F, which is equivalent to 15. We know that already. So 8 plus 4 plus 2 plus 1 makes 15, which is F. Again we have 9, which is, we'll write down the place values, 1 2 4 8. 8 and 1 makes 9. So our binary number is going to be this, equivalent to 9F2. Moving forward, we have hexadecimal to denary. When we have to convert hexadecimal number to denary, we have to do it with the place values. Now this is the base 16 system, so we have place values 1, 16, 256, 4096, 65,536, and so on. Let's suppose we have this number 1A9B, 1A9B. We have to write down the place values above the number and multiply the number with its place value. So B place value is always, because the first number is always 1 place value, I'm writing place values above it. 1, 16, 256 and 4096. Multiplying this number with its place value, 1 gets multiplied with 4096, then A is actually 10, so 10 gets multiplied with 256, 9 gets multiplied with 16, 11 gets multiplied with 1, because B is 11. We add them, we get 6811. This is a denary number system, base 10. 1A9B was a hexadecimal number system, base 16, so hexa to denary is converted. Moving forward, when you have to convert a denary number system to hexadecimal number system, you have to divide a number by 16. Let's suppose we have a number 746 that we are going to convert into hexa. Yeah, 746 when divided by 16, we have 40, when 16 multiplied by 46, we have 736. So 746 into 16, 746 divided by 16 gives 736, and remainder is 10. So we have remainder A. Again, 46 has to be divided by 16. 16 2s are 32. So we subtract 14 is the remainder. 14 is equivalent to E. And 16, now 2 is not divisible, so 16 zeros are 0 and 2 is the remainder. So we have the number 2EA and we write it upside down like the arrow shows. So we read number 746 decimal number system converted to hexadecimal is 2EA, which is base 16. Moving forward, conversion between bases. If it's difficult to convert from base 16, like if it's difficult to divide number with 16, you can convert that number into binary and then convert binary into hexadecimal, which makes it easy. For example, 746 has to be converted into hexadecimal system and it's difficult to divide number by 16. We will convert this denary number into binary first. So I'm just writing down the place values. 1 2 4 8 16, we've written the place values and we have to see what can be added to make 746. So I've took 512, 128, 64, 32, 8 and 2. When we add all of them, it makes 746. Now this binary, again starting from the right side, making groups of 4, I converted this binary into hexadecimal. So now 8 and 2 makes 10. This is 10, which is equivalent to A. 8, 4 and 2 makes 14, which is equivalent to E. And this is 2. So 2EA is the number base 16 converted by this process.